In a previous radiological example, we updated a transfer coefficient matrix by merging individual short-duration high-split dispersion simulations to create a single air concentration output file. During that discussion, it was noted without explanation that during a real-time event, HYSPLIT can be configured to provide a continuous update to the transfer coefficient matrix with each new forecast cycle by using the particle positions from the end of the last simulation to initialize a dispersion forecast. In this example, we will review a modification of that script to provide daily updates to the dispersion forecast to simulate a continuous source event. This presentation is a supplement to the online pages at www.hysplit.com/utility/tcm_daily.html and the corresponding bash shell script tcm_daily.sh. The primary focus of this discussion is to provide a more detailed understanding of how the script works and therefore how you could adapt it to other situations, as almost any real event will require some customization. One advantage of the transfer coefficient matrix approach is that we can compute updates to the plume position as new forecast data become available, or update the emissions as more details of the event become known, without having to recompute the dispersion from the start of the event. The way the transfer coefficient matrix works can be illustrated by an example spreadsheet. Each square with a number represents a 6-hour dispersion calculation segment. The emission time period is from the 7th through the 10th of the month, covered by 3 48-hour meteorological data forecasts, each available at 00 UTC. These specific days have no special significance. They are just the days I happen to download the forecast meteorological data. The segment with the emission is represented by the green square. So to start, on the 7th at 00 UTC, noted as 700, we have the first calculation. After 6 hours, all the particle positions are output to a file. At 7:06, the 7th at 06 UTC, we start a new emission, the green square, but also read the particle position file from the 700 calculation. And this will continue the calculation for the 700 release. At this stage, there are now 2 calculations. This process continues using the meteorological data from the 7th until the last emission period is computed for the 8th at 18 UTC. The numbers in each box represent the meteorological forecast data, that is, for the 7th, 8th, or 9th, that is used for the computations in that segment. At the end of the 8th, there are 8 independent calculations using the meteorological forecast from the 7th, only one of which represents a new emission. When the meteorological data from the 8th become available, we go back and use the 4 particle position files created for the 4 releases on the 7th and valid at 800 to recompute all the segments starting at 800. but now using the meteorological forecast data for the 8th rather than for the 7th. This process of repeating the calculations with more recent data continues until the meteorological data are no longer updated. The forecast meteorological data files, HYSPLIT.t00z.namsf.netile, used for the simulations shown here, are no longer available on the server, ftp.arl.noaa.gov/pub/forecast, because all forecasts are deleted after a few days. However, the script should work without modification with any sequential series of 0Z forecasts. The forecast files should be renamed to the standard name used in the script with a common base name, initial forecast day, and with the cycle time as the suffix. For instance, base day.t00z. For this example, the original radiological script is simplified to show the transport and dispersion of a non-depositing inert gas, and it is now called tcm_daily.sh. The link to the script can be found on the web page, HYSPLIT.com, referencing this video. Before discussing the details of the script, I want to repeat the overview of the computations. For this hypothetical event, a continuous emission is assumed, which is divided into 6-hour computational segments. The event starts at 00 UTC, 7 January 2023. The script is run 3 times, once each day when the new 00 UTC forecast becomes available. Each daily forecast is expressed as an air concentration output and extends out to 48 hours. On the second day, the 4 emission periods that occurred on day 1, 0 to 6, 6 to 12, 12 to 18, and 18 to 00, are continued into day 2 using the meteorological data from 00 UTC 8 January, replacing all the previous output files from 8 January that had used the previous forecast data. During the day 2 simulation, the day 1 output files, those for the 7th, are not affected. The process is similar for the day 3 simulation, starting on the 9th, where the day 1 and 2 results are unaffected, but the new 48-hour forecast extends out through 10 January. This sequence can continue for the entire duration of the emission event, well beyond the 3 days shown in this example. At the start of the script, enter the 2-digit year, month, and day of the 00 UTC forecast that will be used in the calculations. A 1- or 2-digit input is acceptable. The initial simulation question is the most important. Yes means it is the start of the event, and all the temporary and intermediate files from any previous calculations will be deleted. A no response means that this is a continuation of a previous event. A continuation means that the list of the simulation start times from all the previous days will be copied to the start_list.txt file. These are the simulations that will be initialized from their particle files and continued into the new forecast period. Also, all of the new emission start times will be added to the list as the script is executed. The script then proceeds in a manner similar to all other HYSPLIT scripts, configuring the required input files, ascdata.cfg, setup.cfg, and any internal script variables. The emission location can be set to any location covered by the meteorological data. The simulation duration can be changed, but it should correspond with the number of simulations per day, which is hardwired into the script to ensure a continuous emission. Note that in a subsequent script section, the output averaging interval is also set to 6 hours. However, that value is independent of the simulation duration, but it should be less than or equal to the duration. The setup.config namelist file should contain the variables needed to ensure a sufficient particle release rate given the duration of the emissions and the resolution of the concentration grid. In addition, the particle positions should be output to a file at the end of each simulation, which we have defined earlier to be 6 hours. Also, in this case, we are using a regional meteorological extract, so that particles will be terminated when they reach the grid boundary. For simulations using global meteorological data, but where the interest may still be regional, it may be desirable to define a maximum particle age with the variable kh_max. The next section of the script defines a loop where each iteration represents a new emission start time within the 2-day forecast period. If the run duration were to be changed from 6 hours, then a corresponding change is required in the start times for the hour loop. Within that loop, there are 2 parts. In the first part, HYSPLIT may be run multiple times. There is one simulation for each previous emission as tabulated in the file start_list.txt. The second part consists of just one more simulation for the new emission that corresponds to the day and hour iteration of the loop. Once a new emission has occurred, its start time is added to the start_list.txt file. New emissions only during the start day are also added to a file called start_previous.txt. Expanding further on those 2 parts discussed above, there will be 2 control files, one for each part. In the first, the particle restart simulation, no new particles are released, and the release rate is 0 for a duration of 0 hours. Any particles in that calculation would have been carried forward from the previous calculation for the release start times defined in the start_list.txt file. In the second part, the control file defines a new particle release with a unit source rate for 6 hours. In both parts, the name of the concentration output file, starting with CG_, should reflect the release time and sample start time, but in the first part, the release day and hour is taken from the list of previous emissions, the prun variable, while in the second part, the release day and hour is equal to the sample start day and hour. At the end of every simulation segment, a particle output file needs to be created. This file will be used to initialize the next simulation in the time sequence for that release. In the script described here, computations are performed at 6-hour intervals. In the first 6 hours, there would only be one simulation. Between hours 6 and 12, there would be 2, a continuation of the 06 simulation, and one with new emissions. During hours 12 to 18, there would be 3 simulations, 2 continuations with no new emissions, and again one with new emissions. The continuation simulations are initialized with the particle output file from its release time predecessor. At the end of each HYSPLIT simulation, for both Part 1 or Part 2, the pardump output file is renamed to correspond to the emission time for that simulation. Prior to every restart simulation, the particle output file for that release time needs to be renamed to the default name par_init, which is used to initialize HYSPLIT. In the situation where the script is run for the first time for a release, Part 2, particle initialization, is not needed. Previous simulations from Part 1 are identified by the day-hour written in the start_list.txt file, which is then used to identify the correct file to open. This works fine for the initial execution of the script. However, on the second execution of the script, when new forecast data become available, the contents of all the pardump files will reflect the particle positions plus 48 hours after the start of the event, while in our case, we are restarting the script at plus 24 hours. Therefore, we retain the particle position data for each simulation prior to starting HYSPLIT by copying each file to a standard name, PP for particle position, corresponding to the release and sample time. The PP files, the particle position files, are used at the beginning of the script to ensure that each restart simulation listed in the start_list.txt file contains the particle positions that correspond to the respective release and simulation start time. The 6-hour simulations for each release and sampling period for the above example would have created 136 concentration output files, which represent 16 release periods over 4 simulation days, the 7th, 8th, 9th, and 10th. In the next step, these files are combined into one file per release period that contains all the sampling periods. This is accomplished by using another loop to go through each release time and find all the sampling files for that release time, and then use the standard HYSPLIT library program, con append, to merge the files in the list to a single file named tg_month, day, and hour. There will be a total of 16 tg files, one for each release time. A simplification introduced into this script demonstrates how one could apply time-varying emissions. In this case, con append is run with a concentration multiplier value, script variable emit, which is read from a file named emit_month, day, hour, where the date field corresponds to the emission time. This file is created after each new unit source release HYSPLIT simulation. In this example, each file contains a release amount of 10 to the 12th micrograms, which would result in air concentration output of micrograms per cubic meter. In a real event, the creation of this file would be disabled, and values for the real event would be provided instead. The final step is to merge the individual release files into a single file using the program con merge. The result is a single file called HYSPLIT.bin that contains all releases and sampling periods using the defined emission profile. Note that because all calculations were done using a unit source emission rate, it is trivial to replace the emissions with corrected emissions and recompute the air concentrations for the entire period without having to rerun the dispersion calculations. The simplest approach would be to create a modified version of the script without the HYSPLIT calculations to just recompute the air concentrations from the existing CG files. For this example, the script was run 3 times. Initially for 7 January 2023, and then again for the 8th, and the 9th. The output graphic from each simulation contained 8 frames at 6-hour intervals out to a plus 48-hour forecast. The graphics illustrate the nature of the output product. The first is from the simulation starting on the 8th. The last frame of the graphic, a plus 42-hour to plus 48-hour forecast, representing the time period 1800 on the 9th through 0 on the 10th. The second graphic is from the simulation using the forecast data from the 9th, showing the same output time period, 1800 on the 9th through 0 UTC on the 10th, but this time it is frame number 4 of the output graphic, representing the plus 18 to plus 24-hour forecast. There are some slight differences between the shorter and longer forecast time products. This video described how a transfer coefficient matrix can be computed incrementally as a pollutant release progresses, updating the particle positions from previous releases with each meteorological data update. The update process is trivial to parallelize because each HYSPLIT dispersion simulation is independent of the others, and they can be computed simultaneously on multiple processors. Note that the example script is only a template that still requires some customization for a specific event.